Alright, we're back from the break and time for another homework review video. Today we're going to be talking about the second half of the Chapter 5 homework, which dealt with a lot of different types of stoichiometry problems, specifically those involving molar or mass amounts of reactants and products. So we had a lot of different variations on that theme, and I'm going to go over some of the problems that we had the most difficulty with, and which should give us a pretty good overview of the types of problems we'll see on this section of the exam. So when we do stoichiometry problems, they can be classified in a lot of different ways depending on the the quantities that were given, but the concept remains the same, which is that we need to use mole ratios of reactants and products to convert between them, and we have to operate in moles when we're doing those steps because the coefficients in chemical reactions tell us relative mole amounts of everything that's involved. So this first question was by request of a student, and we had only about a 50% success rate on it anyway, so I definitely want to go over this one. So ethyl alcohol in gasohol burns to form CO2 and H2O. If the combustion reaction consumes 5.395 moles of C5HW2z, that is the ethyl alcohol. We didn't learn about nomenclature yet, but that's what that means. And if it's reacting with excess O2, how many grams of H2O are formed? So anytime we're doing a stoichiometry problem, we have to have a balanced reaction. No questions asked, no shortcut around that. So we need to write a balanced reaction. We're told that a combustion reaction here forms CO2 and H2O. We should be aware of that anyway without being told that. So we have C2H5OH is what we're burning. The other reactant in a stoichiometry, in a combustion reaction is O2, and that's going to form CO2 and H2O. So we need to balance this reaction. Now it turns out for this problem we don't need to have it perfectly balanced because we just need to know the ratio of H2O to C2H5OH. We're only talking about those two things. As long as we have those coefficients correct, we'll be fine, but we can go ahead and balance the whole thing. So when we're doing combustion reactions, the easiest way to balance them is to balance the right side first. So we're going to set this to 1, and we're going to balance CO2 and H2O accordingly. So our reactant has 2 carbon atoms, it's C2H5OH, so we're going to make 2 CO2s, and then our reactant has 6 hydrogens, H5OH, so 5 plus 1 is 6 total hydrogens, which means we need 3 waters. Now we also need to balance the O2. It's in excess here, so it doesn't really matter that much, but if we wanted to balance that, we have, on the product side, we have 4 plus 3 is 7 O2s. We have 1 in our reactant, so we need to have 6 more from O2, so we put a 3 out here. That gives us a total of 7 oxygen atoms on each side. So that's the full balanced equation. We don't have any fractional coefficients this time, so that makes our life easier. And now we're ready to go ahead and start the problem. So we're looking for the grams of H2O that form in this reaction. So that's what we're solving for, and we're given an amount of C2H5OH in moles. Now very often our first instinct is to convert moles into something else, but remember, for stoichiometry problems, this is what we need exactly. So very often we're given a mass amount. We'll see those later on, but here we're just given the moles, so we're ready to go ahead and do the conversion. So we have moles of C2H5OH, and we're trying to find an amount of water that's being formed. So we're going to convert moles of that into moles of water by using the mole ratios. So 3 moles of H2O is going to form for every 1 mole of C2H5OH that reacts. That comes from the coefficients in the balanced reaction. 3 H2Os, 1 C2H5OH, and then finally we have to convert into mass of water. We're not given the molar mass of water, we need to determine that here. So the molar mass of water is 16.0, which is the atomic mass of oxygen, plus 2 times 1.008, which is the atomic mass of hydrogen, and that gives us 18.02. That's one we'll see a lot, so if you convert now into grams, 18.02 grams of water per 1 mole of water. We can check all of the units that we don't need, cancel out up to this point, and that gives us into grams of water. So when we multiply that across, we get 291.6 grams of water. And I think this was a numerical answer problem, so you would only enter in the number, and you would want to enter it to the specified number of digits that we tell you in the problem. but here's the answer in terms of 4 significant digits. Okay, so that's how we do this problem. And like I said, this is a mole to mass problem because we're given moles of one species in the reaction. We're asked to find the mass of another species. And in this case, it actually reduces the number of steps because we don't have to convert this initial amount here into anything else. It's already in moles for us, so we can go ahead and use the mole ratio directly. All right, and then we have sort of the opposite type of problem, which is mass to moles. Here we're given the mass of a reactant, and we're finding the mole. Sorry, we're given the mass of a product and asked to find moles of a reactant. So here we have the reaction of N2 and H2 to produce NH3, one of the most industrially important reactions in the world, as it turns out. And we want to know how many moles of N2 will produce 43 grams of NH3 if sufficient H2 is present. All right, so we always have to have a balanced reaction, so we'll start with that. N2 plus H2 going to NH3. Okay? So fairly simple reaction. Then to balance it, again, we can set our most complicated species to 1, which would be NH3 that has 2 different types of elements in it. So we'll set that to 1. We have 1 nitrogen, so we need 1/2 N2. We have 3 hydrogens, so we need 3/2 H2. Now, if you're bothered by fractional coefficients, this form will work here. We can use fractional coefficients in stoichiometry problems. There's nothing wrong with that. But if you don't like to have them, we can just double all the coefficients in this reaction, and that will give us a form of the reaction that has whole number coefficients. N2 plus 3H2 goes to NH3, 2NH3 it should be. Okay, so that's the form of the reaction without fractional coefficients, which we find more convenient to use. So we're trying to find how many moles of N2 will produce 43 grams of NH3. So that's our given information. We're trying to form that much product. We want to know how much of the reactant do we need. And we're told that sufficient H2 is present. So what that means in other terminology is that H2 is in excess, which means we don't have to worry about the amount of H2 that's present. We're only trying to find how much N2 is required, assuming we have enough H2 to do the reaction in full. Alright, so to do this, we just have to set up our calculation now. So we're looking for moles of N2, that's what we're trying to find. And our given amount is 43 grams of NH3, which we're interested in forming. Alright, so the first thing we have to do in a stoichiometry problem is convert into moles. Before we're in moles, we can't really do anything else. So here we're given a mass, so we have to use the molar mass to convert into moles. So the molar mass of NH3 is 14.01, which is the atomic mass of nitrogen, plus 3 times 1.008, that's the atomic mass of hydrogen, as we saw before. And so that gives us 17.03, I think it is. Yeah, 17.03 grams per mole. Okay, so that's the molar mass of NH3, so we're going to use that to convert into moles of NH3. So 1 mole of NH3 has a mass of 17.03 grams. So grams of NH3 cancels out. And now we can use stoichiometric coefficients to convert into what we're looking for, which is the amount of N2, how many moles of N2. Okay, so we have, from the balanced reaction, a mole ratio of 1 to 2 for N2 to NH3. So for every 2 moles of NH3 that are formed, it requires 1 mole of N2 reacting. And here we now stop. Again, very often we would convert this into a mass amount or some other amount, but the question is asking us for moles of N2. Always check for what the question is asking you, and then stop there once you get there. Don't do any extra steps that are unnecessary. So we convert into moles first, then we use the mole ratios, and we should get 1.26 moles of N2. Okay, so that's how we do that problem. It's just sort of the opposite of what we did before, a mass to mole calculation. Alright, and then finally, probably the most common type of stoichiometry problem is mass to mass. Specifically, if we're going into the lab and doing stoichiometry, if we're doing a chemical reaction in the laboratory, mass is the most convenient measurement for amount of substance that we have in the laboratory. So more often than not, we're going to be taking mass of some reactants and figuring out how much mass of product can form, or vice versa. So this is going to be the most conventional one that we'll have to see, is mass to mass. Alright, so here we're combusting 4.56 grams of C4H10, and we want to know how many grams of CO2 that will yield. So for this, we do need to know what exactly a combustion reaction is. This is, at this stage, the only type of reaction we have to worry about. We're going to learn a bunch more this week in Chapter 6. But if we have C4H10 as our reactant, the combustion reaction involves reaction with O2, and the only two products that we get in a combustion reaction are CO2 and water. Alright, so we saw this in the first example, and so we're going to write out this reaction, and then we have to balance it before we start anything else. So our reactant has 4 carbons, we need to form 4 CO2s, and then our reactant has 10 hydrogens, which means we form 5 waters. That gives us a total of 13 oxygen atoms on the product side, which means we need a 13 halves O2 if we want to balance that. Now again, if fractional coefficients bother you, we can always get rid of those by multiplying by 2. We have to multiply every coefficient by 2, and that gives us this form of the reaction: 2C4H10 plus 13O2 goes to 8CO2 plus 10H2O. Doesn't really matter in this problem, especially because we're not even interested in how much O2 is involved. So having a fractional coefficient in front of O2 is definitely not going to cause us any problems, but if you want to get rid of them, that's how we do it. Okay, so we can use either form of this reaction, either with or without fractional coefficients, and now we can start the calculation. So we're looking for how many grams of CO2 form, and we have 4.56 grams of C4H10. So we first need to convert that into moles before we can use stoichiometric ratios. So to do this, we have to get the molar mass of C4H10. We always need molar masses if they're not given to us. We have to calculate them. So the molar mass for C4H10 is going to be 4 times the atomic mass of carbon, which is 12.01, and then 10 times the mass of hydrogen, which, as we've seen before, is 1.01. So that gives us somewhere around 58.14. Alright, so that means 1 mole of C4H10 is a mass of 58 grams, which we can now use in this first step here to convert into moles. So 1 mole of C4H10 is a mass of 58.14 grams. One thing to keep in mind when we're doing stoichiometry problems is we don't worry about the coefficients in the balanced reaction until we've converted into moles. So when we're converting into moles, this first step here, using the molar mass, it's just 1 mole of C4H10 per 58.14 grams. We don't worry about the fact that our balanced reaction has a 2 in front of it at this stage. But now that we're converting into moles of a different species, here we're looking for moles of CO2 in this first step. Now we're going to use the mole ratio, and that's where the stoichiometric coefficients become important. So 8 CO2 forms for every 2 C4H10s that react. So we're going to use that ratio, 8 moles of CO2 for every 2 moles of C4H10 that react. So moles cancel out, grams cancel out. So now we're in moles of CO2. We're asked for grams of CO2, so we need to use the molar mass of CO2 to get that. So going up to the top here, the molar mass of CO2, since it's not given to us, is 12.01, which is the mass for carbon, plus 2 times 16, which is the mass for oxygen. So that's going to be 44.01 grams per mole. So if we're doing a mass-to-mass stoichiometry problem, we need 2 molar masses because we're converting from mass to moles and then back into mass at the end. So 44.01 grams of CO2 per 1 mole of CO2. Remember that the molar mass is the mass of 1 mole, so there's always going to be a 1 mole in that conversion factor. And that gives us into grams of CO2, so when we multiply this across, I didn't work this out beforehand, so give me a second. We get 13.8 grams of CO2. And it says, and the problem says assume 100% yield. So this is the maximum amount of CO2 that can be formed in this reaction. Okay. Alright, so that's a typical mass-to-mass stoichiometry problem, but for this one we also needed to generate the balanced reaction, which was a combustion reaction, and we have to know how to do that as well. Alright, then finally the other type of stoichiometry problem that we'll often see is a limiting reactant problem. So remember, the way we identify a limiting reactant problem is that we're given amounts of two different reactants, or two or more, I guess I should say. So if we're given the mass or the moles of two different reactants, we need to figure out which one is limiting reactant, which is going to determine how much of the product can form ultimately during the course of the reaction. Alright, so here we have calcium reacting with sulfur to form calcium sulfide. Now there's actually one thing we haven't really talked about in this class is standard states. Sulfur is actually S8. That's going to be the standard form of sulfur, elemental sulfur. But whether we realize that or not, it doesn't make a difference in this reaction. We can just assume that sulfur is either S or S8. So most of you probably just balance the reaction like this: calcium plus S going to calcium sulfide, and this will work just fine. So it doesn't matter whether you have S as S8 or not, because the coefficients still work out. You can verify that for yourself if you want. So we could balance the reaction like this, or it could be 8 calcium plus S8 going to 8 calcium sulfides. Either way, the math will work out the same, as it turns out. So it doesn't matter how you balance this reaction, but I'll just stick with the simpler form here, which is probably how most of you did it anyway. Okay, so what is the theoretical yield of calcium sulfide that could be prepared from 3.25 grams of calcium and 2.33 grams of sulfur? So we have masses of two reactants, so we need to figure out which one is the limiting reactant. So remember that the way we do this is we first convert them into moles, and then we divide by the coefficient to get what's called the stoichiometric ratio. So if we do this for calcium, we have the moles of calcium is going to be, we have 3.25 grams and we use the atomic mass of calcium from the periodic table. That's going to be 40.08. Alright, so we get 0.0811 moles of calcium Alright, and then we need to find the stoichiometric ratio for calcium. Whoops. So the stoichiometric ratio, which I abbreviate R, is going to be this number divided by the coefficient for calcium, which is 1. Okay? And then we do the same thing for sulfur, for the other reactant that we're given. So we have 2.33 grams of sulfur. For assuming just sulfur by itself, S, we just use the atomic mass of sulfur, which is 32.07. So 1 mole of sulfur has a mass of 32.07 grams. And that gives us 0.727 moles of sulfur. And the stoichiometric ratio is just that number divided by the coefficient, which again is 1 in this balanced reaction. Okay, so because sulfur has the smaller stoichiometric ratio, this R value here is smaller for sulfur than it is for calcium, this is going to be our limiting reactant. Okay, so sulfur is a limiting reactant, which means that when we're calculating the mass of product, the theoretical yield, that's just the amount of product that could be formed in this reaction if all of the limiting reactant is consumed. When we calculate that amount, we need to use the amount of sulfur as our starting point, because that's the limiting reactant. So we're looking for grams of calcium sulfide. Now we already calculated moles of sulfur, so we can go ahead and use this amount as our starting point, since that's going to be the first step in our calculation anyway. So 0.727 moles of sulfur. We go to the balanced reaction. It's a 1-to-1-to-1 reaction, so very simple in this form. So that's going to be 1 mole of calcium sulfide forming for every mole of sulfur. And then we just use the molar mass of calcium sulfide, which is the sum of the atomic masses, so 40.08 plus 32.07. So to convert into mass of calcium sulfide, 72.15 grams per 1 mole. And we get 5.24 grams. And again, because this was a type of question where you have to type in our answer, we just put the number, no units at all. Alright, so this was a mass-to-mass stoichiometry problem. We had to take the additional step first of determining the limiting reactant, because we have to know which one of those is going to dictate the amount of product that forms. So don't forget to do that step. If you're given masses of 2 reactants, or any amounts of 2 reactants, you need to figure out which one is the limiting reactant. Okay? Alright, so coming back now to another limiting reaction problem. This one was a little bit more conceptual in nature. We're given a multiple choice question. So we have 0.1 moles of SaO2 and 0.2 moles of HF combined in this reaction. So they react to form SiF4 and water. And we want to know which of these statements is false. We have 5 statements here. We have to determine which one is false. So we're going to have to sort of go through each of them and address them one by one. So the first one deals with the limiting reactant. HF is a limiting reactant. So to find the limiting reactant, we have to determine the stoichiometric ratios. Again, that's the way I like to do it anyway. So the stoichiometric ratio for SiO2, remember, it's the moles of that reactant divided by its coefficient. So we're told directly in the problem that we have 0.10 moles of SiO2, and then its coefficient in the balanced reaction is 1, so it has a stoichiometric ratio of 0.10. And then we do the same thing for HF. So we have 0.20 moles of HF, but its coefficient is 4 in the balanced reaction that we're given. So that means its stoichiometric ratio is 0.05. So that means this is the smaller value, so that's going to be the limiting reactant. So choice A is true. And if choice A is true, then choice B must also be true. So choice B says some SiO2 will be left over. If HF is the limiting reactant, that means SiO2 is the excess reactant. Whatever is not limiting has to be in excess. And so that means some of it will be left over at the end of the reaction. So this is also true. So choice A and B either have to both be true or both be false. They can't have one be true and one be false. They're sort of dependent on each other. And now for choice C, the theoretical yield of SiF4 is 0.10 mole. So let's just determine that. Okay, so HF is our limiting reactant, so we need to use that as our starting point. So the moles of SiO2 that form, SiF4, SiO2 is our other reactant. The moles of SiF4, silicon tetrafluoride, that form, we started with 0.20 moles of HF. So once we're doing these sort of calculations now involving a limiting reactant, we don't use the stoichiometric ratio, we use that actual molar amount, 0.20 moles of HF, and then we just use stoichiometric ratios to figure out how many moles of SiF4 can form. So that has a coefficient of 1, so 1 mole of SiF4 forms for every 4 moles of HF that reacts. That's the coefficient in front of HF. So our theoretical yield of SiF4 is actually only 0.05 moles. So it looks like choice C is false. So that's the front runner right now. Now let's verify that choice D and E are true. So choice D is just a conceptual question, or conceptual statement. More HF would be needed to ensure that all the reactants are used up. And this is true because HF is our limiting reactant. So if we want all of the reactants to be used up, we need to add more of that to consume the excess SiO2. Okay, so choice D really just tests our understanding of the definition of limiting reactant. And then finally, choice E deals with a theoretical yield of H2O. So if we're looking for the moles of H2O that can form in this reaction, we again start with the moles of HF. Sorry, I forgot to write it up there. So 0.20 moles of HF is our limiting reactant. And then the amount of H2O that can be formed, we have a coefficient of 2 in front of H2O. So 2 moles of H2O forms for every 4 moles of HF that reacts. And so 0.2 times 2 over 4 is going to give us 0.10 moles of H2O. So choice D and E are true as well. So the only false statement in this bunch is choice C, which is the answer we should have picked. Alright, so this took some doing because we had a lot of statements to go through, some of them conceptual, some of them numerical. But the numbers here were pretty simple. We were given moles of reactants, and so we and just asked about moles of products, so we just used the stoichiometric ratios. Just a single step. Alright, and then finally one more sort of conceptual stoichiometry problem. And I think part of the difficulty here was just formulating a balanced reaction. So the circles below depict reaction between AB2 and B2. If 5 moles of AB2 reacts with 3 moles of B2, how many moles of B2, if any, would remain unreacted? Alright, so there's a lot going on here. I think this was a multiple choice question, but I'll just give you the answer anyway, and it'll correspond to that answer choice. Alright, so we have to figure out what the reaction is we're talking about here, and that's really the only purpose that these pictures serve, is to determine the reaction. So we can surmise, using a little bit of logic, that since the reactants are AB2 and B2, that means A is going to be represented by the larger black sphere, and then B is going to be represented by the smaller orange or brown spheres. And then if you look at our product side, so these are reactants, which are, as we're told, are AB2 plus B2. If we go to the product side, the only new product to form, the only new species that's in there looks to be AB3. So there's one black sphere with 3 brown spheres around it. So our products are AB3. So that's really the only new thing that forms on this side. So that's going to be the only product of our reaction. So because this is a limiting reactant problem, we need to have a balanced reaction. And so to do this, we have AB2 plus B2 going to sorry, my tab was processing. Alright, going to AB3 is our only product. To balance this, we put a coefficient of 1/2 in front of B2, and then we can double the whole thing to give us a balanced reaction without fractional coefficients if we prefer to do that. So 2 AB2s plus B2 going to 2 AB3. Okay, so this is our balanced reaction. Now we can figure out what the limiting reactant is. So we have 5 moles of AB2, 3 moles of B2. So we have to figure out the limiting reactant. We figure out the stoichiometric coefficient, stoichiometric ratios. So that for AB2 is going to be the number of moles, which is 5, divided by its coefficient, which is 2. And then the stoichiometric ratio for B2 is going to be, we have 3 moles of B2, its coefficient is 1. Okay, so that means the AB2 is our limiting reactant because its stoichiometric ratio is 2.5 as opposed to 3. So AB2 is limiting, which means we are going to have some excess B2, and we want to know how many is unreacted. So the moles of B2 that are consumed in this reaction we know that we have 5 moles of our limiting reactant, which is AB2. And then the balanced reaction tells us that 1 mole of B2 reacts for every 2 moles of AB2, which means we're going to consume 2.5 moles of B2, which means that our excess B2, we have 3 moles of B2 to start with. We're reacting 2.5 moles. And that's going to give us 0.5 moles, which was one of the answer choices in this problem. Okay, so we have 0.5 moles of excess B2. So in this case, for an excess reactant problem, there is one additional step. So in addition to finding the limiting reactant, which we always have to do for given amounts of 2 reactants, we then find out how much of the other reactant is consumed and then how much is left over by subtracting from the initial amount. Alright, so that takes us to the end of this homework review. A lot of these stoichiometry topics are going to come up again and again, even in Chapter 6, just with a slightly different twist to them. So make sure you're very clear on mole ratios and all these other important concepts dealing with stoichiometry, and we'll continue on with that this week. Alright, have a good week.